Welcome to the Elon Musk Signal channel. Rocket engines, silent warriors on the journey to conquer space. Every time the roar of the Raptor engine resounds, a new mission begins, and recently, we witnessed the spectacular launch and landing of the Starship. I've watched that impressive performance many times. However, everything is not yet perfect. As you can see, a Raptor engine suddenly shut down. What happened? Let's follow this video to unveil the mystery and discover surprising truths about the Raptor, as well as SpaceX's challenging journey in building the Starship rocket. Rocket engines play a crucial role as the driving force propelling the rocket through Earth's atmosphere. Their power and reliability are decisive factors in the success or failure of the mission. Recognizing this importance, SpaceX, the pioneering aerospace company, has set out to build the most powerful rocket engine for the Starship, largest spacecraft ever built. That engine is called the Raptor. However, achieving perfect operation for the Raptor as desired by SpaceX has not been easy. Despite ending with a spectacular landing, the journey of Starship's mission to Mars on its latest flight was not entirely smooth. From the moment Starship lit up and left the launch pad, issues emerged. The graph in the top left corner of the screen showed an outer ring engine suddenly shutting down after only 5 seconds. Although SpaceX has not elaborated on this incident, some hypotheses can be made. Looking back at the troubles with Raptors in previous Starship launches, in the first launch, several Raptor engines stopped functioning midway. SpaceX quickly investigated and identified the main causes leading to many Raptors shutting down mid-flight. The key parts related to the malfunction include the propellant feed system, fuel pumps, hot gas manifold, hydraulic cluster, and ignition system. Under the harsh operating conditions of the engine, these components could not withstand, leading to fuel leaks, engine shutdowns, and irregular ignition. To address these issues, SpaceX has continuously improved the engine design. The propellant feed system, fuel pumps, and hot gas manifold have been reinforced with better heat-resistant and corrosion-resistant materials to prevent cracking and fuel leaks. The hydraulic cluster has been replaced by an entirely new electronic TVC system, enabling more precise and reliable engine control. Finally, the ignition system has also been upgraded to ensure all engines start evenly and at full power. These improvements have led to the success of Starship Flights 2 and 3, where SpaceX completely resolved engine failure issues right after liftoff. Therefore, we can trust that the Raptor engine shutdown in the fourth flight may not be related to engine design, but could be due to another cause. The biggest suspicion currently is related to fuel delivery to the engine during launch. Although SpaceX had previously announced hardware changes to address fuel flow issues for the fourth test flight of Starship, it seems this issue has not been completely resolved. This indicates that SpaceX's Raptor engines have not yet fully demonstrated reliability. However, fourth flight of Starship was still a brilliant success. The engines operated powerfully, creating a rare diamond-shaped exhaust plume. Flexible engine control, shutting down and restarting engine clusters, pushed the Super Heavy booster back to Earth, a remarkable technique. The shutdown of one engine may be just an isolated incident due to a blockage of the liquid oxygen filter flowing into the Raptor engine, and it did not significantly affect the Starship's flight process. This is an advantage of SpaceX using dozens of small engines instead of just a few large engines for its rocket. Through the troubles of the Raptor engine, we can see that engine manufacturing has been complex. But controlling engines to operate normally and stably is even more complex. Engines can shut down at any time, or even fail to ignite. The necessary conditions are not met during startup. So what makes rocket engines so difficult to ignite? The answer depends largely on the type of engine. Typically, the more complex the engine, the more difficult it is to reignite. The only exception is solid fuel engines, which cannot be shut down in the usual way once activated. Firstly, it's important to note that rocket engines require the input pressure into the combustion chamber to match the pressure exiting through the nozzle. Otherwise, the burning gas will flow back into the tank. This is why 95% of the complexity of rocket engines comes from figuring out how to efficiently pressurize the fuel to the appropriate level. However, there are also rocket engines that start extremely simply, requiring only the turning of one or two valves. These are called pressure-fed monopropellant engines, often used for reaction control system (RCS) to perform maneuvering operations in space. The reason they are so easy to start is because they are essentially just one or two pre-pressurized tanks connected to valves and nozzles. When the valve is turned, compressed gas will escape, creating thrust. They are called pressure-fed engines because the fuel inside the tank is pre-pressurized to the required pressure when exiting the nozzle, so no fuel pumps are needed. In fact, pressure-fed engines can achieve even higher efficiency when using decomposable fuels such as hydrogen peroxide, generating heat during decomposition. In terms of complexity, they are still similar to the previous type, just with the addition of a combustion chamber placed between the valve and the nozzle. To achieve even higher efficiency, engineers use bipropellant engines, utilizing the properties of hypergolic fuels. Simply put, self-igniting fuel mixture is a combination of two gases that can spontaneously combust upon contact. So you don't need any ignition components. Just open the valve, and the engine will self-ignite and operate. However, things become more complicated when we go beyond the scope of bipropellant engines. The problem lies in the fact that this type of engine is limited by the maximum pressure that can be contained in the fuel tank, which must be designed as light as possible. The alternative solution is to use pumps to pressurize the fuel to high pressure. This is a method used throughout the history of spaceflight, with countless variations. However, the pump system is also the most expensive part of developing a rocket engine, and is the main reason why starting most of these engines becomes difficult. So how does SpaceX ignite their rocket engine? SpaceX uses self-igniting fuel like TATB, a mixture of triethyl aluminum and triethyl borane, to activate the engine. For example, SpaceX's Falcon 9 rocket uses TTB to ignite the Merlin engine. As oxygen starts to flow in, TTB self-ignites, initiating the combustion process in the engine. This method is lightweight and extremely reliable, but the downside is that it is costly and requires refueling after each use. SpaceX's new generation Raptor engines use a different method. They use a torch igniter system, also known as an augmented spark igniter. This system works similarly to a gas lighter, but instead of igniting directly, it uses a small igniter to ignite the methane LOX mixture to maintain a pilot flame. Basically, it's a miniature rocket engine activated by the main igniter. Pilot flame will maintain combustion throughout the ignition process, providing a stable flame source for the engine. Through this learning journey, we can see that developing rocket engines is an extremely complex task. In addition to manufacturing high-performance engines, controlling the ignition process, regulating, and shutting down are also challenging problems that require careful calculation. Thank you for watching the video. Let's look forward to the next grand events together. Leave your comments about today's broadcast. Don't forget to like, share the video, and subscribe to the channel to stay updated with interesting information. Goodbye and see you in the next video.